All right, so the Bohr model said what really is happening in the atom of any of these elements is that, you know, we got this nucleus in the middle, and then outside of the nucleus, we have electrons floating about in orbits, in different orbits, and the different orbits have different amount of energy. So kind of think of like our solar system, where like the sun is in the middle and then the planets orbit the sun. So we could say like this is Mercury, Venus, Earth, Mars, and so on. So this is how Bohr explained what was happening in the atom. And they said we had this dense, this is still the nucleus here, and we could say, oh, this is n equals 1, which is like level 1. This is n equals 2. This is n equals 3, like orbit number 1, orbit number 2, orbit number 3, orbit number 4. And the electrons were on any one of these different orbits, just like the planets are on any one of these different orbits. And so they're still attracted to the positively charged nucleus. You know, the electrons have negative charge. But he said what happens is when an electrical current, say for instance, runs through neon or mercury or hydrogen, one of these lamps, what happens is the electrons jump from one orbit to the next, and they can't go in between, but they go from one orbit to the next. And let's say, for instance, I'm an electron and I jump from level 1 to level 3. Let's say I get enough energy to jump me from level 1 to level 3. What happens then is like instantaneously, the electron falls back down, and when it falls back down, it emits light. So that's how he described the emission. And we say now that the emission is like saying when an electron moves from a higher energy level to a lower energy level. Are you guys following me so far? From a higher energy level to a lower energy level. So basically, he's saying that it's like when an electron goes from n equals 3 to n equals 1. That's what emission was. And conversely, on the other hand, absorption was when an electron went from a lower level to a higher level. So basically, an electron would absorb some energy and jump to a higher level, and then it would instantaneously fall back down to a lower level. And when it fell to a lower level, we call that emission. When it jumped to a higher level, we call that absorption. You guys follow what I'm saying? Give me a thumbs up. Give me a
Yes, kind of. Yeah, we're
electrons moving from a lower level to a higher energy level. And saying basically it's like from moving from n equals 1 now to n equals 3.
All right, that's called absorption?
Yeah. So it's basically saying it absorbed some energy and it was able to move the electron to a higher level. And then when it instantaneously fell back down, it emitted that energy, and that energy was given off as light. So we say when it's emitting energy, it's going from the electron is basically going from a higher level to a lower level. And when it's absorbing energy, the electron goes from a lower level to a higher level. Whether it's from 1 to 2 or 2 to 1, it doesn't matter, or 1 to 4 or 4 to 1, it doesn't matter. Now, what ends up happening is the Bohr model sounds good, but it only sounds good because it only explains the hydrogen atom. So the issue with the Bohr model is that the Bohr model only explains the emission spectrum of the Bohr model. I'm sorry, of the hydrogen atom. Meaning it could only really explain why hydrogen emitted that pink light. It didn't really, when you do all the calculations and the higher level physics and chemistry, it didn't really explain why all the other atoms emitted the color of light that they did. So that's how the quantum mechanical model came about. Now the Bohr model is still important, and we still talk about the Bohr model because you guys understand this picture that I just drew. Like you understand, okay, you got the nucleus, you got the different energy levels, just like with our planets. But then when you talk about the quantum mechanical model, it's much more deep than this. And this is just a good visual. The Bohr model helps you like get into the quantum mechanical model. So remember, the quantum mechanical model tries to do the same thing that the Bohr model did, but it's a little more complicated, and it basically talks about orbitals versus orbits. So remember, I'll draw this up here. The Bohr model said that the Bohr model called these orbits. And when we switch over to the quantum mechanical model, we're going to describe orbitals. So let me talk about the quantum mechanical model right quickly, and then we'll take a break. And then I'll come back and talk about electron configuration. All right, so the quantum mechanical model basically describes orbitals. These orbitals do not have a set specific path. Or do not have a set specific path. Meaning they're not like these orbits that are just a set orbit that I drew out here. They're really detailed and really quite complicated. The issue is we found out that you could never really know where the electron is and how fast that it's going at the same time. And so these orbitals just give a probability of where the electrons reside. So the orbital just gives a probability because you don't ever really know exactly where the electron is going to be. All right, so if we have these orbitals that give the probability of where the electron resides, we can describe these orbitals using what is known as quantum numbers.
It says does not have a specific, I'm sorry, what does that say? Path? Or
Yeah, path. It says it doesn't have a specific path. Orbitals are just saying they're gonna give you a probability of where the electron is. You never know exactly where the electron is, but it's gonna give you like a probability map of where the electron could be, to where you can like zone in on where it is, like in a small area, but you don't know exactly. So to understand these orbitals, we use what is known as quantum numbers. And I'll just say describes the orbitals. All right, so there's 4 different quantum numbers. We're only going to talk about 2 of them in this class. And just so you get a basic understanding of what the quantum numbers are. So the 2 quantum numbers I want to talk about, the first one is the principal quantum number. The principal quantum number is given by the letter n. It's a lowercase n. Thanks. And it basically determines the amount of energy in the orbital. Basically, it's like the size of the orbital, like how big the orbital is. So when we talk about the principal quantum number, we're saying that, first of all, we describe it by the letter n. N can be equal to any integer. Basically 1 through infinity. So 1, 2, 3, 4, 5, all the way to infinity. That symbol represents infinity. So if I'm in, my principal quantum number is 1, that means I'm smaller than 2. 2 means I'm smaller than 3. 3 means I'm smaller than 4. 4 means I'm smaller than 5, so on and so forth, which also in turns means that I have less energy. So electrons in energy level 1 have less energy than those in energy level 2, energy level 3, energy level 4, and 5. It's kind of like if we look at the Bohr model, it's kind of saying like n equals 1 has less energy than n equals 2, which has less energy than n equals 3, which has less energy than n equals 4. And you can see that because the further away from the nucleus they get, the bigger they get. Okay, you guys following me so far with the principal quantum number?
So basically it could be any number, right?
It can be any number. The higher the number, the more energy it has.
The higher, okay.
All right, so the other, and so I'm calling this principal quantum number in our book. I think it also calls it the principal level. So another word for this is the principal level. I'll say that as well. They mean the same thing. All right, and then the second quantum number that we're going to talk about is the subshell, or another way of saying it is the sublevel. So one's like the main level, and then there's the sublevel. And the sublevel we designate with the letter L, and it determines the shape of the orbital. The L also equals an integer, but this time the integer starts at 0 and goes all the way to n-1. So 1, 2, 3, 4, all the way to n-1. So the sublevel is always going to be 1 less than n. Now, because these are both integers and you don't want to get those confused, a lot of books use letters instead of the numbers for L. So for instance, if I'm saying L equals 0, that simply, we're going to use a letter to designate it. That letter is S. And we're saying that the sublevels, remember the L describes the shape of the orbital. An S set shape, or L equals 0, means that it's in the shape of a sphere. So I'm writing this is a sphere. And there's always only one S-shaped level per energy level. So meaning, if I'm in energy level 1, I can say that there's only one S sphere-shaped orbital, is what I'm saying. If I'm in energy level 2, there's only one sphere-shaped orbital in energy level 2. In energy level 3, there's only one sphere-shaped orbital in energy level 3. And so let's say, for instance, this is energy level 1. I'm going to call it the 1s. It's in the shape of a sphere. The 2s is going to be a little bit bigger because it has higher energy. The 3s is going to be a little bit bigger because it has higher energy. And they're all in the shape of a sphere, is all I'm getting at. And then if I say L equals 1, we're going to call the p orbitals. And the p orbitals are in the shape of a dumbbell. And the dumbbell, remember, just think of like a dumbbell weight. Looks like this. And there are 3 p-shaped orbitals. There's always going to be 3 of them. So when I'm talking about the P shape for, let's say, energy level 2, they're going to have 3 P-shaped orbitals at energy level 2. And we call these the 2p orbitals. When I get to energy level 3, there's going to be 3 P-shaped orbitals, but they're going to be a little bit bigger than the ones in energy level 2. You guys follow what I'm saying with this? We call these the 3p. And you can go on to 4s and 4p, 5s and 5p. There is no 1p orbitals, and that's mainly because this goes to n-1. So there's no 1p, p starts at 2, which means it starts at energy level 2. And I'll explain this more when we come back from the break. But let me just tell you what each number represents. If I say L equals 2, that means I am now a d orbitals, and they're in the shape of a clover. And there are 5 d-shaped orbitals. And then at 3, we say that these are F. We give them the letter F, and we can't really draw out their shape. It's a complicated shape. I'll say that. But just know that there are 7 F orbitals.
So all these go to these specific numbers that the arrows are coming from?
Yeah, so just so you don't get these integers confused with these integers, they use letters to designate these integers now.
Okay.
So sometimes I'm giving you both ways because sometimes they go back and forth depending on who's asking the question. So if they'll say in sublevel 0, and if I only showed you that sublevel S, you're like, what's sublevel 0? I'm telling you sublevel 0 means they're talking about the S sublevel. Sublevel 1 means they're talking about the P sublevel. But we're mainly going to use the letters S, P, D, and F. All right, so these are the two quantum numbers that we have to know for this class. Remember, the quantum numbers explain or describe the orbitals to where the electrons reside, and it just gives us like a probability map of where the electrons are going to be. So for instance, I'm saying, okay, if I say my electrons in the 1s level, that means in the shape of a sphere somewhere in the atom and closer to the nucleus, I can find the electron there. Versus if I say my electrons in the 3p, this is also around the nucleus, but we can find it in here. And I'll show you guys images of this to make it a little bit more clear. Let's see. Like I said, it ends up involving a higher level math. So for instance, I'm saying, if I were to zoom in on the atom, this is like the probability of finding the electron. This is where I would find the electron on the XYZ plane. Remember, this is three-dimensional space here. This is where I would find the electron, and we could designate that as, okay, it's gonna be in the shape of a sphere, so we call this the 1s orbital. So this is what happens for each orbital. It's like the electron has a probability of being in certain area, and those certain areas form a different shape, is what I'm getting at. If we talk about the p orbitals, it's like, okay, the probability of finding this electron, it's gonna look somewhere in here, and we can say this is more of like a dumbbell shape, so we call these dumbbell looking shapes the p orbitals. Okay, so are you guys following what I'm saying? I know it seems all kind of new stuff and a little complicated, but I'm just giving you the basics of it. The whole point of all of this is that we're just trying to figure out where the electron's going to reside, so we can zoom in and say, okay, I know that the electron here in fluorine is going to be in the 2p whatever. You guys follow what I'm saying? I'm going to talk about that in the second half of class. So right now,
No.
yeah, I know it gets a little crazy, but we're going to talk about the electron configuration when we come back. But before we get there, do I have any questions so far?
So basically, the bigger it is, the bigger the number is, right?
Yep. The higher, the more energy it contains, the further away from the nucleus it's going to be.
Okay.
All right.
Numbers that are written, like how dumbbells 3, clovers 5,
Mm-hmm.
that's just how many of the actual shapes there are.
Yep. So it's saying there's only one shape per energy level that's in the shape of a sphere. But there's 3 different shapes per energy level that are in the shape of a dumbbell. And there's 5 different shapes in each energy level that's in the shape of a clover.
Okay.
Okay. So.
And 4 is n minus 1, right? Or no?
No.
There's no shape for 4?
Yeah, we don't get to 4. We're not, it's the shape
okay.
more and more complicated. So these are the easy shapes that we can easily determine, and I can talk about where these atoms are with these shapes.
Okay.
Okay. So let's take a break. Let's take like a 15-minute break. What time is it? So maybe 2:25. We'll start back up, and then I'll go through electron configuration and make all this relate to the periodic table. All right?
All right.
I'm pausing. And let's get through this. So remember, the whole point of this is we're trying to say where the electron resides in the atom. Modern day times, we use the quantum mechanical model. The quantum mechanical model consists of orbitals. And we use quantum numbers to describe the orbitals. Remember, this orbital just gives a probability of where the electron is going to be. This is the point of all what I'm saying. So the 2 different quantum numbers that we need to know in this class is the principal quantum number, which we describe as n. And then the second one is the sublevel or the subshell, which we describe as L. We're going to use letters for L and we're gonna use numbers for n. So if you're taking notes, I say just grab a whole new sheet of paper, and we're gonna start our whole new sheet of paper, and I'm gonna draw out a little diagram or table for you. So we're gonna start off with the principal shell or the principal level. We're gonna start, I'm gonna say this is the principal. We're gonna call this either the level, the shell, we call it the principal shell, the principal number. This is basically what energy level we're in. It's designated by the letter N. All right, and then the next column we're gonna say is the number of subshells. And
And that's number 17, right? Is that 17 or is that a nucleus?
this is N, this says N.
Oh, and okay, sorry.
I'm saying when I talk about the principal level or the principal shell or the principal number, I'm talking about N. It's basically saying what energy, I'll just say this is like the energy level. And then the number of subshells, I'm saying we're calling this L, or the subshell letter is another way of saying it too. Here, I'll make them two different columns. I'll say subshell letter. And I'm saying that this is L. All right, so a couple different things is one that when I draw a box represents an orbital. This half arrow, whether it's up or down, represents an electron. And in each box, the maximum amount of electrons we can have is 2, and they have to be in opposite directions. So they have to be one's facing up, one's facing down. Max of 2 electrons per orbital. All right, there we go. All right, so if we start off with n equals 1, n equals 1 has 1 subshell in it. I'm not trying to confuse it. It has 1 subshell in it, and that 1 subshell has 1 orbital. And that orbital is called the 1s orbital. When we go to n equals 2, n equals 2 has 2 subshells. The 2 different subshells that they could have are the S and the P. So the 2 different subshells they can have are the S and the P, and we would say one of the orbitals is called the 2s because it's an energy level 2, and the other orbitals are called the 2p. Remember, when you talk about the p orbitals, there's always 3 of them.
I thought the P's were dumbbell shaped.
They are, but I'm saying just in general, when I represent each orbital, like the S is still a sphere shape, but I'm just drawing a box to represent each orbital. I'm not actually drawing the shape of it.
Okay, got it.
But yeah, you're right. They are dumbbell shaped. It's like a dumbbell across the x-axis, then one across the y-axis, and then one across the z-axis. If we think of x, y, z planes. All right, then I get to energy level 3. When I'm at energy level 3, yeah, I'll write it over like this. Energy level 3 says that I have 3 different subshells. So if you haven't noticed, the number of subshells depends on the energy level. Energy level 1 has 1, energy level 2 has 2, energy level 3 has 3. So if I was on energy level 8, I'd have 8 different subshells. So I have 3 different subshells. Those 3 different subshells, there is energy level 3 has a 3s. It has the 3p. So 1, 2, 3 for the 3p. And then it has also the 3d, and d orbitals, there are always 5 of them. 1, 2, 3, 4, 5. 3d. And then finally, because we're only going to go to energy level 4 and not even really, I'm just going to write it out because I'm going to relate this all to the periodic table. In energy level 4, I have 4 different subshells. Those 4 different types of subshells or 4 different types of orbitals. I have the 4s. There's only one of them. I have the 4 p's. 1, 2, 3. I have the 5 d's. 1, 2, 3, 4, 5. And then I have the 7 f's. So 1, 2, 3, 4, 5, 6, 7, and these are the 4 f's. I need a pencil. Thanks. Where's that pencil you guys had yesterday? You know? Pencil that could write. That was the day ones. Yeah. All right, guys, we have all this drawn out. Now let's pull out our periodic tables. If we pull out our periodic tables, I'm going to relate each atom and where their electrons are from the periodic table. All right, so I'm just going to go from left to right. And from left to right, starting off with element number 1. We know element number 1 is hydrogen. So how many electrons does hydrogen have, guys? Do we remember? How many? I heard you say it, I just didn't hear what you said.
1.
1
plus.
Hydrogen's number 1 on the periodic table. It has 1 electron. It has 1 proton. We know this atomic number tells us the number of protons, but to get the number of electrons, remember the positive has to equal the negative, so the atom will be overall neutral. So if it's just a neutral atom of hydrogen, we say it has 1 electron, 1 proton. Same thing with all the other atoms. However many protons they have, that's the same number of electrons. So if we're talking about hydrogen, the way we write out its electron configuration is, I'm going to write it on a different sheet, but I'm going to go back and forth. We say hydrogen has 1 electron. That 1 electron resides in the very first orbital which is the 1s. So we say the electron configuration for hydrogen is 1s, and there is 1 electron in it. So it's like I drew a half arrow here, that 1 electron from hydrogen. If I start from the very bottom and work my way up, it's in the 1s orbital, and we say the electron configuration for hydrogen is 1s1. And remember, all electron configuration tells us it illustrates the occupation of orbitals by electrons in each atom. So it's just saying, where's that 1 electron for hydrogen? The 1s is the name of the orbital. And then this 1 superscript tells us the number of electrons in the orbital. You guys follow me so far? In that very first box, I put 1 electron. Remember, this half arrow represents an electron. And that very first electron is hydrogen. It's in the 1s orbital. So that means the probability of finding the electron in hydrogen is going to be in a small shape of a sphere. If we go to the next element, element number 2 is helium. Remember, He is number 2. It has 2 electrons. So we get to helium, we say it has 2 electrons. Those 2 electrons, the way we'd say they are is we'd simply, if I just draw another electron here, I'm saying those 2 electrons for helium are still in the 1s orbital, but now there's 2 electrons there.
Wait, why is it in the 2? Why is it in the 1s? I'm sorry.
Remember, we got to have maximum.
Maximum of 2 electrons. Okay.
So I just drew that second electron. Now, when I get to the 3rd electron for lithium, I go to the next level because this orbital is full. So I would say, okay, that 3rd electron, when I get to lithium, lithium's number 3 on the periodic table. We say it has 3 electrons, and I'm simply just filling in from the bottom to the top. So this first orbital is already full. I can't put any more electrons there. My 3rd electron is now going in the 2s. So I'd say the electron configuration for lithium says, okay, those first 2 electrons were in the 1s. So I have to say 1s2. And then that last electron was now in the 2s, so it's 2s1. And we just continue this for all the elements. So when I get to element number 4, which is beryllium. Beryllium has 4 electrons. So once again, the first 2 electrons are always going to be in the 1s. So 1s2, but now when I say 1, 2, 3, 4, now it's 1s2, 2s2 for beryllium. So give me a thumbs up or write in the chat box if you guys are following what I'm saying.
I'm trying to comprehend, but it's not making sense fully to me.
See all these boxes? This boxes is basically saying I got to start at level 1 and fill in these boxes 1 by 1, 2 being the max in each box, and just keep going. If I had 10 electrons, I'd say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's skip ahead. How about that? Let's skip ahead, because when we're at beryllium now, well, let's go to the next one. Let's just keep going in order for a second. So I'm literally just filling up the boxes from the bottom all the way, or like starting with n equals 1 until I run out of electrons. If I look at boron, which is number 5 on the periodic table, boron has 5 electrons. Those 5 electrons, starting from the bottom, from n equals 1, 1, 2, 3, 4, and then I say 5. So when I write out the electron configuration, it's 1s2, 2s2, 2p1. So let me write that out. I'm saying now it's 1s2, 2s2, 2p1. And so if you look, I'm just literally adding on 1 electron to the previous atom. Sometimes that extra electron is going to take me to a different orbital. Sometimes it's just going to say, oh, instead of having 1 in the s, the 2s, I have 2 in the 2s. But pretty much the further down the periodic table you get, these are just going to repeat themselves. So when I get to carbon, let's see if you guys can predict what the electron configuration for carbon will be. So carbon has 6 electrons. I'm just adding 1 more and I lied, sorry guys. The difference is when we get to carbon, when you have orbitals that are all on the same energy level, which means 2p, you know how there's 3 P's, there's 5 D's, and there's 7 F's? You have to fill them in singly first. So I'd have to say, this is 6, 7, and then I come back up and double them. So you'd still write the electron configuration out the same, where it would say 1s2, 2s2, and then 2p2. But the way you draw it in the boxes is you'd have to say single, 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 and then double, double, double. So meaning, if this is 6 for carbon, 1s2, 2s2, 2p2, and then after carbon, there is nitrogen. Nitrogen has 7 electrons. It's still the same thing, 1s2, 2s2, 2p3 now, because the p orbitals can have 6 up to 6 electrons. I'm sorry, yep, 6 electrons, 2, 4, 6. So the way it works is it's saying, okay, this is 5, 6, 7, and then I would say 8, 9, 10. And let me just write it all out for you. So I just did nitrogen, which was 7 electrons. After nitrogen, there's oxygen, has 8 electrons. We'd say 1s2, 2s2, 2p4. Then there's fluorine, has 9 electrons, 1s2, 2s2, 2p5. And then after fluorine, there's neon. Neon has 10 electrons, 1s2, 2s2, 2p6. So what I'm saying is, if I drew out these orbital boxes for neon, the 1s looks like this, the 2s looks like this, and then when I get to the p and draw the boxes, there are 3 p boxes that I always have to draw. And the way I fill them in, these 6 electrons, the way I fill them in is I'd say 1, 2, 3, because they have to be parallel, and then 4, 5, 6. When it comes to 6, you can't really see a difference, but let's say, for instance, we're talking about 5, 2p5, when I draw out these boxes, these 3p boxes, and let me label them. So this is 2p, this is 2s, this is 1s. I'd say 1, 2, 3, 4, 5, like this. If I'm drawing the 2p out for oxygen, it's 1, 2, 3, 4. Instead of 1, 2, 3, 4 is what I'm getting at. Do you guys see the difference in what I'm saying? I have to fill it out singly first and then come back up and double it. With the 2p3, it would look like this. 1, 2, 3. So when I have this table, I'm literally starting at energy level 1 and working my way up. As I get to higher energy levels, the orbitals get bigger and they have more energy in them. And there's a greater probability map of where I would find the electron.
I'm sorry, is that the same way as the 3D? The 3P, I'm sorry?
Yep, so all the P's, if I have, so for instance, it's not the same for the S because there's only one box.
Exactly.
But all the P's have 3 boxes, whether it's 2P, 3P, 4P, 5P. So you gotta go single, 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 and then double, double, double. Same thing
Okay.
with the D's. When you get to the D orbitals, like for instance, when I get here with the D orbitals, I'd have to say 3D 1, 2, 3, 4, 5, and then come back and say 6, 7, 8, 9, 10.
Okay.
Same
Okay.
thing with the F's. Okay, so let me quickly relate this to the periodic table some more. So let me see, let me find a blank periodic table. You guys have a blank periodic table? And let me know if you guys have any questions. I'm just looking for a blank periodic table so I can draw this out clearly for you. I know I have another one printed out somewhere. All right. All right, so if we look at this periodic table, what I just described to you is how the electrons actually fill in, but there's an easy way to look at it on the periodic table. And as we look at it on the periodic table, what we're gonna do is say, this first 2 columns, and I'm gonna draw helium in right here and include it in this first 2 columns. So these first 2 columns, we're gonna call this the S block. And I'm gonna say it's the S block. Remember, the S orbitals have 1 orbital, and the max amount of electrons it can have is 2 electrons. Each row, I'm gonna call N. So row number 1 is N equals 1. I'm saying that this is N equals 2. I'm saying that this is N equals 3. So when we look at hydrogen, we're saying that it's an energy level 1 and it's in the S block and there's 1 electron in it. So the electron configuration for hydrogen, we can easily just look at the periodic table and say that it's 1s1. We don't have to draw up this big old chart and fill in the boxes. We don't have to do all that. We can just look at the periodic table and say that. When we get to helium, we're saying helium is also in the S block, and with it being in the S block, it is still in energy level 1, but we say now it's 1s2. So everything in column number 1 is gonna be S1, and everything in column number 2 is gonna be S2. So lithium is gonna be 2s1, sodium's gonna be 3s1, potassium's gonna be 4s1, this is 5s1, 6s1, 7s1. When we get to helium, it's 1s2. When we get to beryllium, it's 2s2. Magnesium is 3s2. Calcium is 4s2, 5s2, 6s2, 7s2. All right, you guys follow me with the S block?
Yeah.
All right, so that's the S block. Then we come over here and we say we're not including helium. We say all of this, all the way over here, is the P block. So we're still saying like energy level 1, 2, and 3. So remember, this is still n equals 1, n equals 2, n equals 3. So now when we're in the P block and we get to, say, for instance, boron, boron is 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Aluminum, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Gallium, 4p1, 4p2, 4p3, 4p4, 4p5, 4p6. The difference with the P block is that, remember, there are 3 orbitals in the P block, and the maximum amount they can have is 6. So it's saying 1, 2, 3, 4, 5, 6, and it represents the 6 boxes in the P block. 1, 2, 3, 4, 5, 6. So when we look at boron, for instance, we see that boron ends in 2p1 because on the periodic table, that's where it stops. It's in the P block, it's the first column in the P block, and it's on the second energy level, we say 2p1. Carbon ends in 2p2 because it's second energy level in the P block, second column. All right, and that's just for every level. And then when we get to the D block is a little special, but the D block, remember when I talked about the D orbitals, there's always going to be 5 D orbitals. So we call the transition metals the D block, and it represents the 5 D orbitals, 1, 2, 3, 4, 5. And if you look at the transition metals starting here with scandium, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's because there's 5 orbitals and 2 electrons per orbital. So scandium is D1, this is D2, this is D3, D4, D5, D6, D7, D8, D9, D10. All right, so the only thing that you really have to know about the D block is that although this is n equals 3 here, when we talk about the D block comes into play when we drew it out on the table. It came in at n equals 3. There was no D at n equals 2. The D block didn't start until n equals 3. So we say here, this is still n equals 3 for the D. So this is 3D. Yttrium starts 4D. And then this is 5D. And remember, we still have to exert these. Can anyone guess what block this would be? What letter, or what letter we haven't talked about?
60?
No, I'm saying like which letter. So we talked about F and D. So yeah, this would be the F block. We call this the F block. There are 7 different orbitals. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And that's because of the 14 different elements in the F block. Now, most periodic tables put this right here and this right here. So the 14 really is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and not those first 2. All right, so if I am trying to randomly figure out the electron configuration for, let's say, I'm just gonna pick an element, let's say silicone. So if I'm looking at silicone, I'd have to say, starting from the bottom, starting from the beginning, I'd say, okay, 1s2, and I'm going from left to right. So there's nothing on the other side because I put helium right here. So it's 1s2, and then I go to the next level, 2s2, and then I keep going across, and now I'm at the 2p, and I have to complete this row before I get to silicone. So then it's 2p6, and then 3s2, and then 3p2 is where it ends with silicone. All right, so if I write it down, I am saying for silicone, 1s2, 2s2, 2p6, 3s2, 3p2 is the electron configuration for silicone. And I got that from looking at the periodic table by saying 1s2, then I go to the next level, 2s2, then I keep going across, that's 2p6. I have to complete each row, 3s2, and then 3p2.
Are you gonna upload that chart later?
Yeah, I can upload a neater version of it. My child wrote all over this, so I can upload a neater version of it. Okay, so let's see if we can just randomly do one. Let's say, for instance, I wanted to do calcium. Let's see if we can do calcium together. So what do you think, what do you guys think calcium would start off with?
1s2,
1s2,
2s2,
2s2. And calcium's right here, so we're going all the way to number 20.
so 2p6,
2p6,
and then 3s2 again.
yep, 3s2. But we're gonna keep going, because right now you're at magnesium. So
2p6.
and then 3p6, and then what?
4s2.
4s2. So did we get it? So did we get this? I gotta get a thumbs up or somebody write in the chat box.
Yes, I think there's a little more practice.
Yeah, we just gotta do a lot of examples. So let's do one from the d orbitals, because that's the only time it gets a little tricky. We have to remember that although this is n equals 4, when we get to the d orbitals, it's gonna say n equals 3. All right, so let's do one from the d orbitals. Let me, hold on a second, sorry. I know I got this other meeting trying to start. So let me just wrap this up, guys. All right. So let's do one from the d orbitals. The one from the d orbital, let me just pick, for instance, cobalt. All right, so if I pick cobalt, it's gonna say the same thing. All right, so if we start from the beginning, let's just try to call it out really quickly. What do you guys think?
1s2.
1s2, 2s2,
2p6,
2p6,
3s2,
3s2,
3p6,
3p6,
4s2,
4s2,
and then it's 1, 2, 3, 4, 6. D.
uh-huh.
3d7.
3,
Yeah, D7. Yes, there you go.
3d7.
3d7. All right, and just remember, if let's say I was going to For instance, gallium, I'd say 3d10, but then I'd have to go back to 4p1. So the only one that's a number behind are the d orbitals. So these are still 4p1, 4p2, 4p3, 4p4, 4p5, 4p6. Does that make sense? Let me quickly do one from like bromine. If I do bromine, it's all this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10 now, and then I go back to 4p, and that's 1, 2, 3, 4, 5, 4p5. And the main thing I'm pointing out here is that you got to go back to 4 when you go back to the p's. The only one that's one behind is the d. All right. So I think you guys get it. There's a few other exceptions and a few other things I want to talk about, but I do want to wrap this up with this right here. I have a practice worksheet on Brightspace under Chapter 9, the Electron Configuration sheet I posted yesterday. It looks like, it looks like this. Where it has the electron configuration, it gives you a summary saying, don't forget, this is what each energy level is. When you get to the D, it's 3D, 4D, 5D, 6D versus 4, 5, 6, and 7. And then you go back to what the S was to begin with the P blocks. The F blocks are 4F and 5F. It starts at energy level number 4. But when you get to elements here that are in the F block, just skip them. So for instance, let me see an element that comes up that's in the F block. For instance, is number 5 that says 7s2 5f9. You skip that because I'm never going to ask you guys about any elements in the F blocks.